Hello, how are you? Scientific Notation Lecture. This is the second lecture in fluid dynamics. I'm at school. It's a beautiful day. It's about 12:30 in the afternoon. The exam period 3 has just ended. About 45 minutes ago it ended. Beautiful day outside, a little cold, but it's warm in the classroom. So this is going to be a little bit of a review for scientific notation. You know, when you work with very large quantities or very small quantities, you use scientific notation. It just makes it a little easier. So I wanted to use this opportunity to review some very basic scientific notation information. The first one is, when you multiply like bases, 10 to the positive 3 times 10 to the positive 6, that's going to equal 10 to the positive 9. So when you multiply like bases, add the exponents. It's pretty obvious, I suppose. However, it does not necessarily explain everything, because you may have 1 times 10 to the positive 3 or 1 times 10 to the positive 6, and then what do you do with the ones? And so it's a little bit more complicated than that. So what you'll need to do is you'll need to get a calculator. I'm going to use a calculator, the T84 Plus Silver Edition, which is way more than you actually need in this course. You can use just a basic scientific calculator. What makes the scientific calculator scientific, I suppose, would be that, number one, you can do trig functions on it, and number two, you can do exponents, like not 10 to the x, but where you can just press either an EXP key or an EE key, and that key allows you to simply put in the data. So on the calculator, it's going to read, for instance, if you put in that value, let's say we put in 4 times 10 to the 8th. So you would put in your calculator. On the screen, it would read 4, E, 8, and that means 4 times 10 to the 8th. So when you press that EE key, that EE key is a little deceiving because it contains the times 10 already. So as soon as you press that EE key, you're pressing base 10. And then when you put in, for instance, 4 times 10 to the 8th, then when you put in the 8, that's actually the exponent. So when you press that key, you're pressing simply an exponent. Now, if you wanted to simply put in 10 to the positive 3, you'd hit the EE key and you'd put in 8. So it would be E8 or E3. Now this is a picture of the calculator I'm talking about. It's called a TI-84 Plus Silver. All the TI graphing calculators are fairly similar. They're far more than you need, and I'm not kidding. They're way more complicated. I don't know how to use a lot of these functions on this calculator. Well, all you're going to be using today is, if you look at the second column, it starts with mode, and then underneath that is xt theta n, and then down 1, 2, 3, 4, fifth row, second column EE. Well, that's what you're going to be pressing. So let's say we have a problem, 4.5 times 10 to the 8th times 2.8 times 10 to the 6th. Now, be careful here. What you have to do is, that should be negative 8. I don't know if you can see that. Can you see that? Yeah, it's negative 6. So it's 4.5 times 10 to the 8th quantity. You got to make sure that quantity is there. Times 2.8 times 10 to the negative 6th. So what you do with that is you plug in the following. Get your graphing calculator and you plug in to do this problem. You simply go 4.5, you hit the blue second button, and then you say EE, which is the comma button, 5th row, 2nd column, and then you hit 8, and then you hit times 2.8, second, EE, negative, because you're making the 6 negative, so you hit the negative first. The negative is down in the lower right corner where you have the negative in a in a parentheses, and then you hit 6, and then you hit equals. Now, you know, what does this really look like after you're pressing it in? I'll show you that in a minute. So let's just review this for a moment. A lot of students want to say 4.5, and they want to say times, and then they hit 10 to the x, and then they put it in 8. You don't have to go through all of that. You simply press those buttons. So do it along with me. Clear your calculator and put in 4.5 second EE 8 times 2.8 second EE negative 6, and then before you press the equal sign, look and see what is actually there. Look and see what's actually there, and you'll see quite clearly that it looks kind of like gibberish a little bit. So on the next slide, I'll show you a picture of what it should look like. And if it doesn't look like this, don't press the equal sign because you did something wrong. So you get 4.5 E 8 times 2.8 E negative 6. Now, when you use that E button, that's parenthetical. So you don't have to use parentheses here. 4.5 EE 8 is all what they call parenthetical. And 2.8 EE negative 6 is also parenthetical. So you don't have to use any parentheses. And then you hit equals, and it's 1260. Okay? And you'll find sometimes that you'll be putting in scientific notation, but when the calculator does the math for you, it gives it not in scientific notation. So if it's a small enough number, it's convenient enough, you just put in whatever's there. And if it's a very large number, then you just convert it to scientific notation. I don't really spend a lot of time on scientific notation. This is actually a little bit unusual to do a specific lecture on scientific notation, but it's important with fluids, so I'm going to give a refresher. Now, the next rule is what they call a quotient rule. You divide like bases. So 10 to the negative 9th divided by 10 to the negative 5th would be 10 to the negative 9 minus a negative 5. So it would be negative 9 plus 5 would be minus 4. And below that is the actual rule. A to the n over a to the m equals a to the n minus m. Now, another word that might be helpful for you is that when you, let's say we did the former problem and you did 4.5 EE8 divided by 2.8 EE negative 6, why don't we do that? So it would be 4.5, sorry, it would be 4.5 EE, second, EE, 8, and then just hit divided by. You don't have to use parentheses. And then you'd say 2.8, second, EE, negative 6. Now, that should be 8 minus a negative 6 would be 8 plus 6. So that should be 10 to the 14th. So you get 1.607142857. So just 1.6. 2 significant figures are fine. So it would be 1.6 times 10 to the 14th. So you should try that. You know, stop the video, rewind, and see if you can do that. Okay? Now, another rule which I think is really important, and that's the reciprocal rule. When you take, now listen to this carefully, this is a little weird. When you take the reciprocal of a base, you take the additive inverse of the exponent. So a, 1 over a is the base. So base, so I'm going to take the reciprocal of 1 over a, and that's a. So the additive inverse of n will be negative n. The additive inverse of positive n is negative n, etc. So look over this particular diagram and you'll see specifically how important it is for you to use this rule. This will be a very important rule when you do conversions. You learned conversions as if it were dimensional analysis. I am sorry to inform you, but dimensional analysis is not unit label conversions. There is certainly a concept of analyzing the dimensions in a conversion, but by itself, that exercise is called factor label conversions. When you analyze the dimensions, like for instance, what are the dimensions of newtons? The newton is kilogram meter per second squared. What are the units for energy? Joules. Well, it's going to be kilogram meter squared over second squared. What are the units for momentum? Kilogram meters over seconds. Though that's dimensional analysis. So, but when you're doing conversions, and I'll show you on a slide that's coming up, it's pretty, these rules are very, very helpful to estimate what your answer is going to be. You may even, not even really need to use a calculator. But if you do use a calculator and it doesn't jive with your estimations, then hey, either your estimation is wrong or your calculator is wrong. Another rule is, what does that exponent mean? So I have a, look at the bottom one, a to the fifth is a times a times a times a times a. So you take 5 a's, right? So 10 to the fifth is 10 times 10 times 10 times 10 times 10. How many zeros are there? Well, there are 5 zeros. So it's an easy way to realize it. So 10 to the fifth means 1 and that many zeros. Look at 10 to the 0. Well, 10 to the 0, how many zeros are there? Well, the exponent tells you how many zeros there are. Well, there's none. So you just put 1. So a to the 0 equals 1. Any number, any number, pick a number. 14,340,863 and 280,453, 100,000 units, and all raised to the exponent 0. Well, the answer is 1. So anything. If I take a chair and raise it to the exponent of 0, the answer is 1. So that exponent, look and see what that exponent really means. What does it mean? Well, 10 to the 0, we work with base 10. Scientific notation is working with base 10. So 10 to the 0 means there's a 1 and 0 zeros. 10 to the 1 means there's a 1 and 1 0. 10 to the 2 means there's a 1 and 2 zeros, etc. Now, scientific notation, by the rules of scientific notation, did you realize that scientific notation has actual rules? According to the rules of scientific notation, you can only place one significant figure to the left of the decimal, and then all the rest of the significant figures to the right of the decimal. How many significant figures are there? Well, you utilize significant figure rules. So 4.5 times 10 to the 8th times 2.8 times 10 to the negative 6. That's 2 significant figures. So it's 1260, rounded to significant figures, 1,300. Look at that last problem that we did. Or 1.3 times 10 to the 3, because you'd only need 2 significant figures because that's as many as you can have. The other problem we did, 4.5 times 10 to the 8th times 2.8 times 10 to the negative 6th, where you had 1.607142857 times 10 to the 14th. Well, there's 2 significant figures in 4.5 times 10 to the 8th, and 2 significant figures in 2.8 times 10 to the negative 6th. So the answer can only be 1.6 times 10 to the 14th. Notice when I say this, there's only one significant figure to the left of the decimal. Now, an application of the rule that the rules we just looked at, if I have 10 to the negative 3 times 1 over 10 to the positive 6th, I could either say that's 10 to the negative 3 divided by 10 to the positive 6, and then you subtract your exponents, and that would be negative 9. Or if you utilize that rule where you had 1 over a to the n equals a to the negative n, you could put in 10 to the negative 3 times 10 to the 6th, negative 6th over 1. So you went from 1 over 10 to the positive 6th to 10 to the negative 6th over 1. Remember, they all have a numerator and the denominator. Any rational number, a rational number is defined as a number that can be expressed as p over q, where both p and q are integers. So 10 to the negative 3 there on the left, 10 to the negative 3, it's really 10 to the negative 3 over 1. So don't be afraid to put in that denominator. So 10 to the negative 3 times 10 to the negative 6, applying the rule, would be negative 3 plus negative 6 would be negative 9. Now, you can actually do that on your calculator. You could put in second EE negative 3 times second EE negative 6, hit equals, and it will be EE negative 9. Okay? So let's actually do an application with unit label conversions. Again, unit label conversions are not dimensional analysis, but we can analyze the dimensions. You want to convert grams per cubic centimeters to kilograms per cubic meter. Now, this is important because, very important because, when we use density, we use kilograms per cubic meter. So you may have to convert. This is the conversion that may not be that unusual. So 1.3 times 10 to the negative 3 grams per cubic centimeter. You multiply by 1 kilogram over 10 to the 3 grams. So the grams cancel. And then you multiply, we took care of the grams, that's in kilograms. Now we want to take care of the cubic centimeters. And 10 to the 6th cubic centimeters in 1 cubic meter. Why is that true? Well, it's really 10 squared centimeters quantity cubed over 1 meter quantity cubed. 1 meter quantity cubed is 1 cubed meter cubed, which is 1 meter cubed. And then 10 to the 6th would be 10 to the 10 squared raised to the 3rd power, so it'd be 10 to the 2nd times 3 would be 10 to the 6th, and then centimeters raised to the 3rd power. And then you're going to cancel cubic centimeters and grams, and that's really your answer. You cancel the cubic centimeters and grams, and then look at the exponents. It's 10 to the negative 3 times 10 to the 6, that's 10 to the positive 3, right? And then 10 to the positive 3 divided by 10 to the 3 would be 10 to the 3 minus 3 would be 10 to the 0. So there are no base 10 exponents. That would be 1.3 times 10 to the 10 times 10 to the 0, which would be 1. So look at below. It's going to be 10 to the negative 3 times 10 to the negative 3 times 10 to the 6th equals 0 or 1. So the answer would be 1.3 kilograms per cubic meter. Okay? That's your lecture on scientific notation. I would suggest reading it and looking at it more than once. Have a great day. Hope you do well on your exams tomorrow, and goodbye.